In this video, we are going to conclude our study of inclusion and exclusion and counting by introducing a few more types of counting problems, including applications of the inclusion-exclusion principle. We already know that many counting problems can be solved using this principle. For instance, we can use inclusion-exclusion to find the number of primes less than a positive integer. We saw an example like that in the previous lecture. Also, many problems can be solved by counting the number of onto functions from one finite set to another. Remember, onto functions, we also use the word surjective. The inclusion-exclusion principle can be used to find the number of such onto functions. Also, there's a famous problem called the hat check problem that asks for the probability that no person is given the correct hat back by a hat check person who gives the hats back randomly. This can be solved by inclusion and exclusion. In this lecture, we're going to focus on an alternate form of inclusion-exclusion that is useful in many applications of counting problems. In particular, this form can be used to solve problems that ask for the number of elements in a set that have none of n properties. So if we list the properties P1 through Pn, and we want to find all of the elements in a set that have none of these properties, we'll first start by letting A sub I be the subset of the larger set that contains the elements with a property P sub I. The number of elements with all of the properties of, here we've taken some subset of the n properties, we'll denote it by n parenthesis and then just pi1, pi2, pik close parenthesis. So this is the number of elements in the set of elements with the properties, and we've just taken some subset of the n properties. In terms of sets, we'll have that the intersection of the A sub I sets corresponding with the corresponding indices to the subset of the properties, the intersection of all of them is going to be the number of elements possessing those properties. So first we think of our entire set, and then we want to find the subsets that contain certain properties, and we want to eliminate those subsets so that what we're left with is just the elements in the set that had none of the properties. So we're going to denote the number of elements with none of the properties using this notation here, where we have P1 prime, P2 prime, Pn prime. So we can think of the prime as kind of like the complement or the opposite or the negation. P1 prime or n of P1 prime would be the number of elements not possessing the property P1. And we'll denote the number of elements in the entire set by just capital N. So then it follows that if we want to find this n sub p, or n of P1 prime, P2 prime, Pn prime, which is the number of elements possessing none of the properties, then we're just going to take the total number of elements in the set and subtract the union of all of these subsets. Remember, the subsets were the subcollections for each property. And we know how to find the cardinality of a union. That's by inclusion or exclusion. So if we just translate it into this new notation, we're saying that n of P1 prime, P2 prime, Pn prime, which is the number of elements from our original set that contain none of these n properties, well, that's going to be the number of elements in the set, n, minus the sum of the cardinalities of the sets for each property individually, plus the sum of the cardinalities where we intersect two sets, so elements that have two properties, elements that have three properties, and so on down the line. Eventually, we'll eliminate all of the properties that we don't want any of our elements to have. So in order to do some of these counting problems, we're going to need a theorem about counting combinations with repetition. So the theorem says that there are n plus r minus 1 choose r many ways, many r combinations from a set with n elements with repetition of elements allowed. So I'm going to introduce this using a simple example, which would be like a cash register. So let's say we have a cash register. Draw a little picture. And it has one space for each of 7 different types of bills. So there's a space for $1 bills, $2 bills, $5 bills, $10 bills, $20 bills, $50 bills, and $100 bills. So here's my cash register. I have 7 different types of bills. And if I was asked how many ways are there to just choose 5 bills randomly from the cash register. So maybe I take 5 $1 bills, that's one way. Or I could take one of each of 5 different types, or I could take a mix and a match. So what this really comes down to is I can think about just these bars dividing the cash register. And then if I was taking a bill out of, say, the $20 bill slot, I would just put a star here. And if I was taking a bill from the $100 slot, I would put a star here. Maybe I put another star here, and a $1 bill, and a $5 bill. So you can see I've put a star in the slot for each bill that I'm taking out of the cash register. Now, if we forget all about the cash register and we just look at this picture, these types of problems will often be called stars and bars problems, because what this really comes down to when we're counting is how many different ways could we arrange these 2 types of symbols. Imagine that one type of symbol is just the bar and one type of symbol is the star. And I have 6 bars and I have 5 stars. How many different ways can I arrange them? Well, the simplest way to count that is going to be to think about this as 11 different spaces. And then what I'm doing is I'm choosing 5 spaces to put the stars in. Do I have 10 or 11? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I need one more gap, one more little space. So I'm choosing 5 spaces to put my stars in this case, in the first space, in the second space, in the 5th space, in the 8th space, and in the last space. And then automatically all of the rest of the spaces get filled by these bars. So the answer to how many different ways can I take 5 bills of 7 types from the cash register is actually going to be 11, choose 5. And that might be kind of a surprising answer because we're not sure how 7 is coming into play here, but it really comes down to thinking about it this way. What I'm really doing is choosing 5 spots to arrange my stars and filling in the rest with the bars. So that gives us this formula. If you think of n as 7 and r as 5, then 7 plus 5 minus 1 is 11. And so it's 11, choose 5. So it's exactly this theorem here. So we're going to remember this theorem and use it in the future. So another example of applying this theorem is how many solutions does the equation x1 plus x2 plus x3 equals 11 have, where x1, x2, and x3 are non-negative integers. To count the number of solutions, we'll note that a solution corresponds to a way of selecting 11 items from a set with 3 elements. So think of x1 as a box, x2 as a box, and x3 as a box, and the way of selecting 11 items. And we want x1 items of type 1, x2 items of type 2, and x3 items of type 3. Then the number of solutions is equal to the number of 11 combinations with repetition allowed from a set with 3 elements. So from the theorem above, that's going to be n is equal to 3, r is equal to 11. So 3 plus 11 minus 1, choose 11, which is 13, choose 11. There are 78 solutions to the equation x1 plus x2 plus x3 equal to 11, where x1, x2, and x3 are non-negative integers. But we can now apply our alternate form of inclusion-exclusion to a problem like this if we add a restriction. How many solutions does this equation have where x1 is less than or equal to 3, x2 is less than or equal to 4, and x3 is less than or equal to 6? So now we're thinking of our larger set as the set of solutions. Remember, there were 78 of those. And we want to exclude the solutions that possess any of these properties. Or rather, we want to count the solutions with these properties, so we're going to exclude the solutions with their opposite properties. So I'm going to let P1 be the property that x is greater than 3. So instead of x less than or equal to 3, I'm going to say greater than 3. I'm going to let P2 be the property that x is greater than 4, and P3 be the property that x is greater than 6. And then I'm actually going to change that up just a little bit to make this a little more straightforward. I'm going to say another way of saying that x is greater than 3 is to say that x is greater than or equal to 4. Again, we're talking about integer solutions, so being an integer greater than 3 is the same thing as being an integer greater than or equal to 4. Being an integer greater than 4 is the same thing as being an integer greater than or equal to 5. Being an integer greater than 6 is the same thing as being an integer greater than or equal to 7. So these are actually the properties that I'm going to use, P1, P2, and P3. And I want to apply my alternate form of inclusion-exclusion to these properties, eliminate them from my total number of solutions, and that will give me the number of solutions that satisfy x1 is less than or equal to 3, x2 is less than or equal to 4, and x3 is less than or equal to 6. Okay, so now we just need to do the counting. So again, we're thinking of these boxes, x1, x2, and x3. And let's look at here n of P1, so the number of elements possessing the first property. And it tells us that's the number of solutions with x1 greater than or equal to 4. So imagine I need to place 11 units into these 3 boxes, but I've already placed 4 in the box x1. So I only have 7 units left to place, and that's why now my r becomes 7. My n is still 3, so I have 3 plus 7 minus 1, which is 9. So this becomes 9 choose 7, and 9 choose 7 is just 9 times 8 divided by 2, 9 times 4, which is 36. All right. Now I want to look at the number of elements that satisfy property 2. The number of solutions with x2 greater than or equal to 5. So now in my boxes, instead of having anything in x1, what I've done is I've placed 5 units into x2 already. So how many units do I have left to place? I have 6. So my r becomes 6. So now my n plus r minus 1 is 3 plus 6 minus 1. That's 8 choose 6, which is 28. And I can do the same thing for the P3 property. P3 is the number of solutions with x3 greater than or equal to 7. So again, I think about, I've already placed 7 units into the x3 box. How many are left to place? 4. So r is equal to 4. 3 plus 4 minus 1. And then choose 4. So there are 15. Next, I'll think about P1 and P2 together. So the number of solutions with x1 greater than or equal to 4 and x2 greater than or equal to 5. So again, I've placed 4 here in x1 and 5 here in x2. How many do I have left to place? That means I only have 2 left to place. So it's 3 plus 2 minus 1, choose 2. That's 4, choose 2, which is 6. If I think about property 1 and property 3 occurring at the same time, that would be x1 is greater than or equal to 4 and x3 is greater than or equal to 7. So I placed 4 there and 7 there. 1, 2, 3, 4, 5, 6, 7. Well, I only had 11 items to place to begin with, so this becomes r equals 0. There are no more items to place. So 3 choose 0, or rather 2 choose 0 is exactly 1. The number of solutions with x2 greater than or equal to 5 and x3 greater than or equal to 7 is 0 because that's impossible. I can't already have placed 12 items because I only had 11 items to start with. And similarly, there are no ways that all 3 properties could be true at the same time because, again, then I'd have 16 objects. I only have 11. So now we can put this all together. We can say the 78 solutions that I started with, then I'm taking out the solutions that satisfy property 1. I'm taking out the solutions that satisfy property 2. I'm taking out the solutions that satisfy property 3. Then I'm adding back in the solutions that satisfy property 1 and 2, and I'm adding back in the solutions that satisfy property 1 and 3. Everything else is 0. And when I simplify, I find that the answer is 6. So there are exactly 6 solutions to the equation x1 plus x2 plus x3 equals 11, where x1 is less than or equal to 3, x2 is less than or equal to 4, and x3 is less than or equal to 6. All right, so one concept that you may or may not be familiar with is the sieve of Eratosthenes. This is an algorithm that allows us to find all of the primes less than a specified positive integer. Using the principle of inclusion and exclusion, we can find the number of primes not exceeding a specified positive integer with the same logic, the same reasoning that's used in the sieve of Eratosthenes. So in case you're not familiar with it, we'll just introduce it here briefly. Recall that a composite integer is divisible by a prime not exceeding its square root. So a composite integer is an integer that's basically not a prime. And we know a prime integer is divisible by only 1 in itself. So a composite integer, therefore, has some divisor other than 1 in itself. And imagine if all of the divisors of a composite integer were exceeding its square root, so say our integer is n, our composite integer, and if all of its divisors were greater than the square root of n, then we'd have something greater than the square root of n times something greater than the square root of n. That would be greater than the number itself. So it's illogical. It's not possible. So we know that for any composite integer, it's divisible by a prime not exceeding its square root. So the first thing that we can do, say we want to find the number of primes not exceeding 100, then first we'll note that the prime numbers, or that any composite number not exceeding 100 must have a prime factor not exceeding 10. So think about that for a minute. Think about what I just said. If you need to pause the video, rewind, think about it again. But it's pretty clear. Any composite integer not exceeding 100 must have a prime factor not exceeding 10. And what we're looking to do is eliminate the composite integers so that we are left with only the prime integers less than 100. So we want to think about the prime integers not exceeding 10. These are 2, 3, 5, and 7. So the way the sieve of Eratosthenes would work is you would write out all of the integers between 1 and 100. I won't write them all, but let's say we write the first 20 or 30. So here we have the first 20, let's do 30. So I would start with the smallest prime integer, which is 2, and I would just start crossing off all of its multiples. Then I'd move on to the next prime integer, and I apologize, we don't want to cross out 2 itself because we're going to circle 2, we're going to keep it. 3 we know is a prime. I can start crossing out all of the multiples of 3. Now right away I can see that 6 is already crossed out. That's fine. I'm just going to cross out 9, 15, and so on. 27. 5 is a prime integer. I'll go through and try to cross out any of its multiples that are not already crossed out, like 25. And then we keep going in this fashion. So in so doing, we would eventually find, let's see, 7 I can cross out 21, excuse me, and now I think everything that's left here is prime. So this is called the sieve of Eratosthenes. We can use this exact same reasoning to apply the inclusion-exclusion. We would say that a property that we're wanting to eliminate is being a multiple of a prime less than 10. So we would want to eliminate all of the multiples of 2, all of the multiples of 3, all of the multiples of 5, and all of the multiples of 7, just as I have done. So we let P1 be the property that an integer is divisible by 2, let P2 be the property that an integer is divisible by 3, let P3 be the property that an integer is divisible by 5, and let P4 be the property that an integer is divisible by 7. Then the number of primes not exceeding 100 is going to be 4 plus the number of integers not possessing any of these properties. Remember, the prime notation means not possessing property P1, not possessing property P2, and so on. Why did we have to add back in 4? Well, because when we subtract out the multiples of 2, the multiples of 3, the multiples of 5, and the multiples of 7, we take with them 2, 3, 5, and 7. So we had to put those back in. There are 99 positive integers greater than 1 and not exceeding 100. A prime integer must be greater than 1, so 2 is the smallest prime. And there are 99 positive integers between 1 and 100. So by the principle of inclusion and exclusion, we would have 99 minus all of the multiples of 2, minus all of the multiples of 3, minus all of the multiples of 5, minus all of the multiples of 7. But then, because some of the integers are multiples of 2 and 3 at the same time, like 6, we've subtracted too many, so we have to add back in the integers that are multiples of 6. add back in the integers that are multiples of 10, and so on. And so you can see here what it would expressly be. It would be 99 minus the floor function. Remember, we talked about the floor function in our previous lecture. The floor of 100 divided by 2 minus the floor of 100 divided by 3. So these are simple enough. We know this is going to be 50, this is going to be 33, minus 20, and so on. Then add back in the number of items with 2 of the properties, subtract the number of items with 3 of the properties, and finally we add back in the number of items with all 4 properties. These numbers are given here, and finally we would determine that there are 21 prime integers not exceeding 100. Then we need to add back in the 2, 3, 5, and 7. So in total 25, because we had to add these back in. So using the principle of inclusion and exclusion, we can replicate this other process. Okay, one other example of an application of inclusion and exclusion that I want to talk about is the number of onto functions. And remember, onto functions are also called surjective functions. And what does it mean for a function to be surjective or onto? It means that every element in the codomain has at least one preimage in the domain. So if you're a little bit rusty now on these terms, codomain, preimage, etc., then you can go back and watch, I think it's our Module 1 or Module 2 lectures, and refresh your memory. So we might want to know, for example, how many onto functions are there from a set with 6 elements to a set with 3 elements? So the solution would be, suppose that the elements in the codomain, there are 3 of them, so let's just call them B1, B2, and B3. Let P1, P2, and P3 be the properties that B1, B2, and B3 are not in the range of the function, respectively. We want to eliminate all of the possibilities where one or more of these elements are not in the range, and by doing so, we ensure that our function is surjective. Note that a function is onto if and only if it has none of the properties P1, P2, or P3. That's what I just said. So by the inclusion-exclusion principle, it follows that the number of onto functions from a set with 6 elements to a set with 3 elements is first the number of total functions between the sets, and then minus the number of functions that miss one element in the codomain, adding in all of the functions that miss 2 elements in the codomain, and subtracting all of the functions that miss 3 elements in the codomain. N, which is the total number of possible functions, is going to be 3 to the power 6, because there are 6 elements in the domain. Each of them must be mapped into the codomain, and I have 3 choices of where I'm going to send it. So I have 3 to the power 6 different possible functions, because I'm thinking of 6 blanks, so 6 elements in my domain, and I can either put B1, B2, or B3 in each of the blanks. So I have 3 to the 6th power many functions. Now, n of pi is going to be the number of functions that do not have b sub I in their range. So then, for a function that's missing exactly one element in the codomain, I have only 2 choices for where I'm going to map each element. So I have 2 to the power 6 functions of this type. And then there will be 3 choose 1 many terms in the summation. So it's going to be 2 to the power 6 times 3 choose 1. That's what I'm going to subtract. Then there's only one choice for the value of a function if it's missing 2 elements in the codomain. So n of pi pj is just going to be 1 to the power 6, or 1. And there are 3 choose 2 many terms of this kind. So that's what I'm going to add back in. 3 choose 2 times 1 to the power 6. And finally, note that there is no function that misses all of the elements in the codomain. We wouldn't call it a function if we didn't assign at least one value to every element in the domain. So n of P1, P2, P3 is going to be 0. So using this line of reasoning, we can conclude that the number of onto functions is 3 to the power 6 minus 3 choose 1 times 2 to the power 6 plus 3 choose 2 times 1 to the power 6. Again, this is all of the possible functions minus the functions that are missing one element in the domain, adding back in the functions that are missing 2 elements in the domain, and then subtracting the functions that are missing all 3 elements, of which there are none. So we find that there are 540 surjective functions from a set with 6 elements onto a set with 3 elements. And this will be a theorem. Let m and n be positive integers with m greater than or equal to n. Then there are n to the m minus n choose 1 times n minus 1 to the m plus n choose 2 times n minus 2 to the m. And following that same pattern, there are this many surjective functions from a set with m elements to a set with n elements. So exactly the same line of reasoning that we just used to talk about that specific example from a set with 6 elements onto a set with 3 elements. You can follow this same pattern for any 2 sets of finite cardinality. Okay, the last new idea that we want to introduce in this lecture is the idea of a derangement. The principle of inclusion and exclusion will be used to count the permutations of n objects that leave none of the objects in their original positions. And such a permutation that leaves none of the objects in its original position is called a derangement. So one famous example of thinking about derangements is the hat check problem. So we are saying a new employee checks the hats of n people at a restaurant, forgetting to put claim check numbers on the hats. When the customer returns the hats, or when the customers return to pick up their hats, the hat check person gives them back hats chosen at random. And the question asks, what is the probability that no one will get back their correct hat? So probability is going to be, in this case, the number of ways that the hats can be arranged so that no hat is in its original position, so the number of derangements, divided by the number of possible permutations, which is n factorial. So this is just the frequency definition of probability. Let me write that down here. Frequency definition of probability. So, as I mentioned, a derangement is a permutation that leaves no element fixed. So one example would be if we wanted to permute 1, 2, 3, 4, 5, then 2, 1, 4, 5, 3 is a derangement. On the other hand, 2, 1, 5, 4, 3 is not a derangement because you can see that the 4 is in the same position as when it started. So we're typically going to use this notation d sub n to denote the number of derangements of n objects. For example, the number of derangements of 1, 2, 3 are just 2, 3, 1 and 3, 1, 2. So there are only 2 derangements. We know that there are 6 permutations of these 3 numbers, but only 2 of them are derangements. And there is a theorem that will tell us the number of derangements. And we're not going to cover the proof in this lecture, but the number of derangements of a set with n elements is going to be n factorial times 1 minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial, and carrying on until we get to negative 1 to the power n over n factorial. So using this theorem, it's very simple to find the number of derangements for a positive integer n. For instance, the number of derangements of a set of 3 elements, we just plug in n equals 3, and that's going to be 3 factorial times 1 minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial, which is 6 times 1 minus 1 plus 1/2 minus 1/6. We end up with 2. As we already said when we discussed the derangements of 1, 2, 3. So now we can solve the hat check problem. The probability that no one receives the correct hat is the number of derangements on n elements divided by the number of permutations on n elements. So d sub n divided by n factorial. So this table shows the probability for different values of n. So if there were two people turned in their hats, and now the hat check person has to give them back, there's a 50% chance that you're going to get the wrong hat. That seems pretty straightforward, right? If there were 3 people, then there's a 1/3 chance that no one is going to get the right hat. If there were 4 people, then the probability is 0.375, which is 3 out of 8, and so on and so forth. So you can see as n increases, we're sort of oscillating around a number that looks like it's 0.368-ish. So when n is 2, it's clearly larger. When n is 3, it's below 0.368. Then it goes back above 0.368, then below, then back above, then slightly below. And using the methods that you may have seen in a calculus class, we can show that e to the negative 1, or 1 over e, is approximately 0.368. Because this is an alternating series, the derangement terms, with terms tending to 0, it follows that n grows without bound. So the probability that no one receives the correct hat converges to 1 over e. In fact, the probability can be shown to be within a very, very, very small margin, 1 over n plus 1 factorial of 1 over e. So that is really cool. Okay, let's do just a couple of counting problems together, and then we'll conclude our section on inclusion and exclusion. The first exercise asks, in how many ways can 7 different jobs be assigned to 4 different employees so that each employee is assigned at least 1 job and the most difficult job is assigned to the best employee? So first of all, let's think about how many total ways can we assign these jobs? Well, first of all, the most difficult job in every possible different arrangement, we want it to be assigned to the best employee. So what we're really going to think about is we've got these 4 employees. Maybe this guy is the best one, and we're going to go ahead and give him the toughest job, whatever that may be. So what we're really doing is we're assigning 6 jobs, the 6 less tough jobs, but we're still assigning them among the 4 people. So the total number of ways that we could assign 6 jobs amongst 4 people would be 4 to the power 6, because we're actually thinking of sort of reversing this process. For each job, I have 4 people to choose from. So I'm actually thinking of the jobs as the blanks. And for each job, I have 4 people to choose from. So let's revisit this. Let's say we started with 7 jobs, 1, 2, 3, 4, 5, 6, 7. And I went ahead and I gave the toughest job to the best employee. So that's taken care of. Now I have these 6 other jobs. I have 4 employees to choose from. For each job, I have 4 employees, so it's just our simple product rule of counting. 4 to the power 6 is the total number of ways. But we had one more restriction. We said how many ways so that each employee is assigned at least 1 job. So we'll convert this to an inclusion-exclusion problem by saying I have 4 employees. I'm going to call them E1, E2, E3, and E4. And E4 is my best employee. So I'm going to put a little star there so I know that E4 is my best employee. I've already given him the toughest job. Then I'm going to say let P1 be the property that employee 1, E1, doesn't end up with a job. So after I assign all the jobs, E1 has no job. I want to avoid this situation, so I'm going to give this property a name. And in fact, P2, if I let P2 be the property that E2 has no job, I'm just going to go ahead and call this PI and EI, just to make the notation a little simpler so I don't have to write the same sentence 4 times, right? So now I want to say, what is N of P1? So how many ways can it be that employee 1 ends up not having been assigned a job? Well, if that were to be true, then these 6 jobs would all be assigned to the other 3 employees. So instead of 4 choose 6, there will be 3 choose 6 ways that this can happen for the exact same reason. I'm assigning this job, I have 3 employees to choose from. I'm assigning this job, I have 3 employees to choose from, and so on. So it becomes 3 times 3 times 3 times 3 times 3 times 3 times 3. And this is also going to be N of P2 and N of P3. Now, N of P4 is 0 because, as we already noted, we gave employee 4 a job because he was our best employee. Now, let's think about N of P1 and P2. So how many ways could employees 1 and 2 both not be assigned any jobs? Well, again, for each job, I'm thinking how many employees do I have to choose from? In this case, I just have 2. I have my best employee and employee 3. The other 2 people aren't being assigned jobs. So there are 2 to the 6 many ways to do that. And again, this is going to be the same as P1 and P3 and P2 and P3. But P1 and P4, P2 and P4, P3 and P4, they're all 0 because I know that property 4 can never be true because employee 4 has already been assigned a job. I'll also think about P1, P2, and P3. How many ways could they all not be given jobs? Well, the only way that that can happen is if employee 4 gets every job. So it's 1 to the power 6, which is, of course, just 1. But if we wanted to look at P1, P2, and P3, or P4 rather, that can't happen, again, because employee 4 already has a job. And P2 and P3 and P4 cannot happen because employee 4 already has a job. Finally, what about P1, P2, P3, and P4? Well, for the same reason, there are 0 ways. So now, the principle of inclusion and exclusion would tell us that we want N minus 3 to the power 6, or the N of P1. So we want to subtract N of P1, N of P2, and N of P3. Then I want to add in the P1, P2s, P1, P3, P2, P3. And then I want to subtract P1, P2, P3. Now, in general, this formula would have all of these other terms as well. But I know that they're all 0. So this is just going to be 4 to the power 6 minus 3 times 3 to the power 6 plus 3 times 2 to the power 6 minus 1. And it ends up being 4,096 minus 2187 plus 192 minus 1, which is 2,100 different ways. So there are 2,100 different ways to assign 7 jobs to 4 employees, with the restriction that each employee be assigned at least 1 job, and that the most difficult job is assigned to the best employee. And we did this using principle of inclusion and exclusion. Okay, the next example is probably a little bit simpler. This is more like what we were doing with our inclusion and exclusion when we were thinking about sets instead of properties, but we can translate this into an inclusion-exclusion question about properties. So first, there are 1,000 applicants for a mountain climbing trip in the Himalayas. 450 of the applicants get altitude sickness, 622 are not in good enough physical shape, and 30 have allergies. An applicant qualifies if and only if the applicant does not get altitude sickness, is in good shape, and does not have allergies. So we can think about does not get altitude sickness or gets altitude sickness as property 1. Not in good shape, property 2. And has allergies as property 3. We want to eliminate these properties. So we want n minus n of P1 minus n of P2 minus n of P3. Then we want to add n of P1, P2, add n of P1, P3, add n of P2, P3, subtract n of P1, P2, P3. So let's see if we can assign these numerical values. Eventually, we want to know how many applicants will qualify. So the total number of applicants, and then we eliminate those who don't qualify. So we know that n is 1,000 applicants. The problem then tells us that 450 get altitude sickness. So I'll subtract 450. 622 are not in good enough shape, so minus 622. And 30 have allergies, so minus 30. Then 111 applicants get altitude sickness and are not in good shape. So they've been subtracted already. I need to add them back in. 14 who get altitude sickness and have allergies, add those back in. 18 who are not in good enough shape and have allergies, so add those back in. And finally, we have 9 who get altitude sickness, are not in good shape, and have allergies. So we want to compute this number. We have 1,000 minus 450 is 550, minus 622, so negative 72, minus 30 is minus 102, plus 111 gives us 9, plus 14 is 23, plus 18 is 41, minus 9 is 32. So out of 1,000 applicants, 32 will qualify. Okay, let's do one problem of the type, how many solutions does the equation x1 plus x2 plus x3 equal to 13 have? And we are restricting it so that x1, x2, and x3 are non-negative integers, less than 6. We remember that these types of problems correspond to choosing 13 plus, so we're going to let r equals 13 and n equals 3. So this corresponds to choosing 3 plus 13 minus 1, choosing 13 from 15. This is the total number of solutions, and then we're going to restrict that number so that x1, x2, and x3 are less than 6. So the total number of solutions is going to be 105. Now, let's let Pi be the property that x sub I is greater than or equal to 6. We want to eliminate all of the solutions with that property, and then what we'll be left with are exactly the solutions where x1, x2, and x3 are non-negative integers less than 6. So n of Pi, this is again a situation where we're thinking about our 3 boxes, x1, x2, and x3. So if P sub 1 is satisfied, then I've put at least 6 units into the x1 box, or if P2 is satisfied, then I put the 6 units in the x2 box, or if P3 is satisfied, then I put the units in the x3 box. So n sub Pi is going to be, instead of 3 plus 13, now I only have 7 units to assign. So 3 plus 7 minus 1, choose 7, which is 927, which is 9 factorial over 7 factorial times 2 factorial, which is 9 times 8 over 2, and that's 36. And the reason I did Pi is because we have the same property for each of x1 and x2 and x3. We want them all to be less than 6. So I don't have to compute it more than once. I just know that it's going to be the same computation for each of them. Then what about P sub I, P sub j? So what about 2 of them are greater than or equal to 6? Well, if 2 of them are greater than or equal to 6, then again, I've placed 6 units in at least 2 boxes, or in exactly 2 boxes. So I've already placed 12 units. So what I have left is just I have 3 plus 1 minus 1, choose 1. So that's 3, choose 1. And 3, choose 1 is 3. This is going to be equal to n of P1, P2, n of P1, P3, n of P2, P3. So they're all the same. And then finally, what about all 3 of them being greater than or equal to 6 at the same time? Well, that clearly can't happen because I only had 13 objects to place to begin with, so there are 0 ways. So now, if I want to find n minus n of P sub I, and this is going to be the sum of all 3 of them, plus n of P sub I, P sub j. This is going to be 1 less equal to I and j less equal to 3. And then minus the triple intersection, P1, P2, P3. Then I should have all of these numbers. This is 105 minus 3 times 36 plus 3 times 3 minus 0, and that is 6. So there are 6 solutions to the equation x1 plus x2 plus x3 equals 13, where x1, x2, and x3 are non-negative integers less than 6. Finally, we want to know how many ways are there to distribute 6 different toys to 3 different children such that each child gets at least 1 toy. This is pretty similar to the first exercise that we did in this lecture note. First of all, let's think about the total number of ways to distribute 6 different toys to 3 different children. So we're going to think about actually each of the toys as a blank. And for each toy, I have a choice of one of 3 children. So there are 3 to the power 6 many different ways, because I could choose the first, second, or third child for each blank, and then apply the product rule of counting to multiply 3 times 3 times 3 times 3 times 3 times 3, 6 times. All right. Then I want to let's say these children are C1, C2, and C3. I want to let P sub I be the property that C sub I does not get any toy. And then I want to make sure that I eliminate all of these cases, and in doing so, I ensure that every child gets at least 1 toy. So n of P sub I is going to be, I'm still assigning 6 toys, but if 1 child is not getting a toy, then I only have 2 children to choose from, so it's 2 to the power 6. And this is true no matter which of the 3 children we're excluding. Then what about 2 children are not getting toys? Well, there were only 3 children to start with, so there's only one way that this can happen. We can think of it as 1 to the power 6, but there's just one way that this can happen. It just depends which child is the only child getting toys. So now we have everything that we need, because we want to compute n minus n of P sub 1 minus n of P sub 2 minus n of P sub 3 plus n of P sub 1 P sub 2 plus n of P sub 1 P sub 3 plus n of P sub 2 P sub 3. And in fact, there is one thing I left out, which would be, how about if none of the children get any toys, then we didn't distribute the toys, so that can't happen. So that's 0. And we would subtract n of P sub 1, P sub 2, P sub 3, but as I said, it is going to be 0. So we have these numbers now. We know that this is 3 to the power 6. N is 3 to the power 6. Then I'm subtracting, this is 2 to the power 6, this is 2 to the power 6, and this is 2 to the power 6, so 3 times 2 to the power 6. And then again, I have 3 times 1 to the power 6, and then 0. So 3 to the power 6, I think is 729, minus 3 times 2 to the power 6 is 192, and then plus 3, and that should give us 540 ways that we can distribute 6 toys amongst 3 children while ensuring that all of the children get at least 1 toy. So that is the last counting problem that I had to show you. So at this point, we've seen lots of different types of counting problems and seen different applications of inclusion and exclusion. So this will conclude our module on inclusion and exclusion, and we will move on to the modules on graph theory next.